when you're just like looking at clips from James's phone is really hard.
Yeah.
But
No,
then I finally got here and I was like, okay, I sort of see, but how do you get from here to here again? Yeah, it was very nice.
That would have been fun for me to test like the quality of those pictures.
Yeah, have
like
you draw
drop you
a
off.
map
Yeah.
based on what you made.
I've seen like sensory tests with Nelly where like someone will draw a photo on your arm and on your back and like reproduce it.
Oh, that's cool.
Yeah. Be a fun
Yeah.
version of that.
Yeah. All right. So we're at time, but we'll wait just a few minutes for people to trickle in. Do any of our audience members want to introduce themselves while we're hanging out and waiting? You know Kevin. Yeah. Same.
Yeah. Recently, everyone's years ago lately.
Was the student today or?
No, so Robbie and I had lunch today.
Yeah.
But
Okay.
so this was the grad student
Grad
meeting?
student
The
Or
grad
ACE.
student meeting and then the ACE lunch is
ACE
tomorrow.
tomorrow.
yeah,
Okay.
any of the ACE students come to lunch tomorrow here?
Yeah.
So we can show up? Okay, yeah. So that's undergraduate students.
Cool.
Yeah.
And when we used to have faculty meetings on Zoom, I would love that we'd always start the meeting at 40 people left late.
Fun. I like that. Give it 2 more minutes. Okay. Do you need anything? Are you water?
Water and stuff.
Okay. And they. Cool. So Lucas is one of the students I was talking about at breakfast who led that SIGSI paper and started ACE. Yeah, he's in the gray.
Oh. We're talking about.
We talked about you at breakfast too.
We've not. My cat said, "Wait, what? You'll pet me?" I have no other goals in life. Like just for a day, I went to my neurologist in the morning, and then at dinner time he came down and started begging for dinner, and I hadn't touched him. So he's like, "Wait a minute."
So has anyone else been watching Severance? I know Sam does, but Ritesh, yeah.
I can't do too much.
So good.
No spoilers. I watched the first episode yesterday, and I'm already hooked. I'm saving it for after 60.
I think I need to rewatch season 1. It's been way too. It's been like what, 3 years? Yeah.
Yeah. So my PhD advisor was a postdoc in that building when it was that last, and now I'm like incredibly jealous of him, just architecturally. I don't think he was severed though, you know, but it's still pretty cool. All right, should we start? All right. Can you hear me up there? Great. Thank you, everybody, and welcome. We're here for David Smith's job talk. He's interviewing for a position as an assistant professor in the Allen School. David is a fifth-year PhD candidate at University of Illinois Urbana-Champaign in the Siebel School of Computing and Data Science. His research focuses on developing and assessing innovative tools and techniques to support novice programmers. He has a BS in computer science from Western Washington University and associate degrees in computer science and physics from Skagit Valley College. So he is very much a local native to here, and we're happy to have him back to give a talk.
Thank you so much. Just to check, lav mic working or? Lovely. Thank you so much, Ben, for the introduction. So let's kick things off by just getting into the executive summary from the talk, what I'm going to be talking about today, and then we'll go from there. So as Ben mentioned, my work is primarily in supporting novice programmers. So I'm going to kick things off just with a broad strokes characterization of computing education research in the context of novice programmers, and in particular highlighting some of the changes we're starting to see given the recent emergence of development of large language models. I'm then going to talk about some of my work in developing a tool that seeks to help students develop some of the skills necessary to engage in human Gen AI collaborative coding. I'm also going to cover some of my work on a tool that most of my work has been done on in a pre-LLM novice programming context back before 2022, 2021, and in particular highlight some of the methodologies that I've used in evaluating that tool, and conclude with some of the big open questions as I see them on LLMs and intro computing, and hopefully reflect on how some of those methodologies could be applied to the creation and evaluation of tools for this new and evolving context. So broad stroke characterization of CS1 or intro computing pre-LLM. Oftentimes when we're discussing intro computing courses, the objectives that we want students to meet can roughly be characterized as being able to produce code independently, or write code, trace code, so give students a set of inputs in some existing code and trace through that code in order to predict an output, and given a set of code, comprehend what that code is doing. And in the context of doing computing education research, in introductory computing, the primary focus of that area had been, for many years, identifying the barriers that students face when acquiring these skills and developing tools and pedagogical approaches that help students overcome those barriers. But as we all know, in 2022, the world changed, or the landscape of development and producing code changed substantially, and it brought friends. And it continues to bring friends. If I was to fill up this screen with every logo of an LLM-oriented company, we'd run out of slides very quickly. So just to, again, broad strokes characterization of what has been happening in computing education research, primarily as it pertains to CS1. We saw the emergence of these models being openly available to the public in 2021, 2022 with GitHub Copilot, Codex, and ultimately ChatGPT. Shortly after that, we saw a lot of the literature that was being published in computing education research venues being kind of a damage assessment, in essence. What things that we've been giving novice programmers can an LLM do? And the answer was pretty much all of them. And then by a year later, it was basically just all of them. And how are instructors and students perceiving the presence of these models? What are their concerns? Moving into 2023 and 2024, there's been a bit of what I would characterize as an evolving sentiment that, Pandora's box has been opened. These models are out there. People can use them. They're going to continue to use them. So our task now is how do we go about integrating LLM and LLM usage into intro computing courses and do that effectively? And how do we teach students to effectively utilize these models? 2025 onwards has yet to be seen, but this seems to be the direction that the area is heading. So, reflecting back again on fundamental skills in CS1, now in CS1 LLM edition, we still have code writing potentially, so we want students to still be able to produce code. We still have tracing because they need to be able to evaluate whether the code produced by the LLM is correct. For a similar reason, we have code comprehension. They need to understand the purpose of the code that's being produced. But we also have this nascent skill of prompting, which is providing a natural language description to a large language model in order to produce code. Some have begun to suggest that code writing might start to receive less emphasis in intro computing courses, and that's something of an open question. How much code do students need to be able to produce independently in order to accomplish their objectives, given LLM's proficiency at doing so? But my work particularly focuses on code comprehension and prompting, where the overarching question that I'm concerned with is how do we help novices develop the ability to understand code and describe code through natural language. Fortunately, there's been a lot of work that existed prior to the emergence of LLMs on this activity, which we refer to as explain in plain English questions. Here, we give students a segment of code. It's a little bit special in that we don't give students useful variable names or useful function names. We give them somewhat obfuscated variable names and function names because we want them to read through that code, understand what it does, and communicate the code's purpose by providing a high-level natural language description of what the code is doing. So this has previously aimed to develop students' code comprehension, or rather evaluate students' code comprehension abilities. But there's a similarity here between prompting and describing code at a high level. So I draw on a lot of work relating to this question and in this space. That said, before the development of LLMs, there were a lot of challenges with giving EIPE questions, or explain in plain English questions, at scale. Namely, they are one of the few questions that we can ask in an intro computing course that requires a natural language response. Code writing questions you can test with test cases. Tracing questions, you can look and see if the predicted output matches what the student predicted the output would be. There has been a lot of success in the development of auto-grading approaches for these short answer questions. So some colleagues of mine developed a logistic grader that is trained on human-labeled responses, EIP responses. And that matches the success of a TA, which does help giving these questions out at scale so students can practice in large quantities and get immediate feedback on that practice. But it does have caveats. It requires a lot of human-labeled data, usually on the order of 600 responses per question that you want to author. And it requires all of this to be created on a per-question basis, which, just given the human overhead in the creation of these questions, is going to act as a natural limiting factor for the diversity of the set of practice questions that you're able to produce for questions for students to utilize. Additionally, given it's a logistic grader, it only provides feedback on whether the student's response was correct or incorrect. It doesn't give, in particular, with respect to a student's incorrect response, the student any information on how incorrect that response was, and perhaps more importantly, what they can do to remediate and evolve that response in order to make it correct. So at a high level, in developing newer auto-graders, the obstacles that previously existed that I'm interested in developing are getting students immediate and actionable feedback on a wide variety of practice activities. So with that said, the question that I went into this project with was, how do we build auto-graders that overcome the obstacles that I just listed? At which point I had a bit of an insight, and that was that prompts for code generation bear a remarkable resemblance to what we expect in an explain in plain English description. Both are natural language descriptions of what code is doing. So the auto-grading approach that I developed, which I refer to as code generation grader, just to go through a pipeline of how a student interacts with this, we show them an EIPE question, just like the example question I showed you a moment ago. They provide their description of what that code is doing. We then hand off that description to an LLM and have the LLM generate some code and run unit tests to see if the code that was produced from the student's description is functionally equivalent to the code that the student was describing. In effect, the grading heuristic here is that if a student's description is sufficient for the LLM to effectively interpret and reproduce functionally equivalent code, we consider that description to be correct. Looking back at the obstacles that I listed a moment ago, it overcomes each in two different ways. One, with respect to providing students feedback, whereas previously we only gave them whether they were correct or incorrect. Now we can tell them give them GPT's interpretation of their description, so they can, in effect, diff the description with diff the generated code with the code that they were attempting to describe, and we also give them the unit tests, which hopefully gives them insight into the space of inputs that we're testing across, and in the event that their description is underspecified, they can see which test cases they passed and which ones they failed in order to go back to their description and further specify it with those edge cases in mind. From the instructor's perspective, the authoring burden of these questions has been reduced because now you no longer need to label a whole bunch of questions. You just have to write some unit tests for the code that you're asking the student to describe, which reduces the authoring burden or the auto-grader authoring burden to being equivalent to a traditional code writing question. Yeah?
This is really interesting, but one question is, different students, kind of especially depending on their backgrounds, maybe where they went to school, might also kind of have different ways to describe the same code. Mm-hmm. And then therefore, some of them might be interpreted more correct than others. Yeah. I don't know if you have seen any of this challenge.
No, we haven't looked into that specifically. Certainly it's an interesting, so I'll get into some analysis that we did of the alignment between this auto-grading mechanism and kind of the traditional grading standards of EIPE questions. I will say in a prior concern of just EIPE in general is the final E. So there'll be this is kind of giving away a little bit of a teaser for the rest of the talk, but given these large language models are trained on such a wide variety of text, I still would, of course, want to do evaluations similar to the ones that you just said, but it does limit my concerns, particularly compared to the logistic grader that I described a moment ago, where that's trained on a very small, very specific set of texts, or a very small corpus of data. So yeah, we haven't done any evaluations, but hopefully some of the alignment between this approach and traditional EIP rubrics might elucidate some of that. Thanks. So yeah, getting into evaluations of these activities. This is still a bit of a new area and an ongoing project, but we've done 2 so far. The first was at University of Auckland, where we were effectively evaluating this as a prototype. I'll get into the details of what we had students do, but this was broadly concerned with characterizing what correct responses looked like under this particular grading approach. Getting some students' general perspectives on interacting with this auto-grader, and in particular, asking students how they interacted with the feedback produced by the auto-grader. At Illinois, which was a follow-up evaluation, we have a variety of auto-graders that we produced, one being the one that I just discussed a moment ago, and we have some data on how students compare their preference between the different auto-graders. So getting first into the evaluation that was done at University of Auckland, this was a very large 800-person intro to programming course for engineering majors that was taught in C and MATLAB. So we ran 2 labs, each of which had 4 EIPE questions that students were asked to solve. These questions were hosted on PrairieLearn, which is a assessment platform that was developed at Illinois. Students were given effectively unlimited attempts to complete all 4 of these questions. We collected data on students' attempts and the responses they submitted, and collected survey responses relating to their perceptions and interactions with the auto-grader that they were filled out after each of the labs. I'll be presenting some descriptive analysis on the characteristics of correct answers under this auto-grading approach and its alignment with traditional EIP grading standards, as well as some of the themes that emerged from qualitative analysis of the students' survey responses. So first, before introducing its alignment with EIPE grading standards, let's first introduce EIPE grading standards. So there's a variety of rubrics that have been used in the literature, but they all tend to go back to the structure of observed learning outcome taxonomy, which is a taxonomy that characterizes the comprehension level demonstrated for a given response and has been adapted for the grading of EIPE questions. So what I and another researcher did was we took a random subset of 1,600 responses that students submitted in the completion of those lab activities, and we coded them according to which category or which level of demonstrated comprehension under this taxonomy that we thought that response fell. So just to walk through these top to bottom, pre-structural and unistructural, which are the first 2 in that bar chart there, these are descriptions that would, under the Solo taxonomy, be characterized as incomplete or fundamentally incorrect. So what we would expect and hope the grading approach would be doing, and that is the automated grader I presented a moment ago, we would expect that responses that we regard as unistructural or pre-structural to be graded as incorrect by the auto-grader, which fortunately the overwhelming majority seem to be. Multi-structural and a slight variant that we came up with, direct recitation, where students were pasting pieces of the code into their multi-structural descriptions, are effectively line-by-line descriptions of code. So these are descriptions that we'd consider to be largely correct, but aren't communicating the code's purpose. It's communicating the code's implementation. And here we see still the majority are graded as correct, but there's a fair number that are graded as incorrect. Not shown here, but anecdotally, we went through these responses, and our hypothesis is that when you give these very detailed descriptions to GPT on how to generate code, the probability of making a minor error that a human might overlook is relatively high, and then the LLM takes you quite literally and generates incorrect code. Now, with respect to relational descriptions of code, which, yes?
Incorrect here, should I understand it? You said students can repeatedly submit. Mm-hmm. So here, this is just a bag of all submissions without factoring in resubmission. Is that correct?
Correct. We didn't do on all submissions just because 800 students times however many attempts. We took a random sample of 1,600 responses.
Sure, but I mean, you're not tracking like how are people modifying it.
Correct. Yeah. This is just a bag of responses that were graded. Yeah. Thank you so much. Yeah. And then finally, for relational descriptions of code, these are descriptions where students are describing a code's purpose. Say, counts the number of even integers in an array, as opposed to describing line by line how that operation is performed. Yes?
Would the students have seen examples, like for other problems, of a high-level description?
Yeah.
So they would have a notion of...
That was introduced in the instructor before the lab activities ran. A short lecture on what EIP questions were and what good responses, canonically good responses, which are relational responses would look like, and helped them differentiate between multistructural and relational. There wasn't an extended introduction to that, since this was fundamentally a lab informative activity for those students. But they had some notion, yeah. Thank you, yeah. And just to cap this off, we see that relational responses are overwhelmingly graded as correct by the grading approach. So there seems to be some alignment. Admittedly, there's this meta problem of a perfect multistructural description will produce correct code and pass the test cases in the same way a perfect relational description will. So we have ongoing work in adding onto the auto grader the ability to differentiate between multistructural and relational responses while still retaining the feedback and authoring benefits. In terms of students' general reflections, they were very positive about these activities, and interestingly, they often spoke to the code comprehension aspect of this, probably in some part primed by the fact it was a code comprehension activity, but they at least reported on finding it useful in comprehending chunks of code and helping them gain insight into the connection between natural language coding, natural language descriptions, and the code that's ultimately produced. And anecdotally, they seem to also find them fairly engaging. Even after correct responses, there were a lot of students just attempting different responses to see if different descriptions would generate different pieces of code. As for their reflection on the feedback, which is the part of this work that I'm perhaps most excited about, in general, students reported on using one mode of feedback or the other kind of in isolation. Rarely did, for whatever reason, did we see students reporting on using both. In evaluating the generated code, they did perhaps what we were intending them to do. This is the student reports. I compared my code to the source code, and after finding the error, i.e. the difference between the generated code from their description and the code they were describing, I changed some of the wording in my prompt. As for how students reflected on evaluating the test cases, one question that students referenced a lot when utilizing the test case mode of feedback was this problem where we were asking students to report, or the code was finding the index of the rightmost zero in an array. And a number of students saw this code and described it as finding the index of a zero in the array, which GPT would generate the code that finds the first zero, the index of the first zero in an array. So as this student reports, for example, 4 consecutive zeros was not anticipated. So they passed all the test cases where there was 1 0 in the array, failed those where there were multiple zeros, and a variety of students, including this one, suggested that the test case was useful in finding that edge case and further specifying their prompt. As for the second evaluation, which was done at UIUC in a large introductory programming course for non-technical majors, we had 4 different auto-graders that we've been using in the course. I won't get into the implementation details of them. The binary grader, for reference though, is the logistic grader that I've referenced previously. 3D grader is a set of 3 logistic graders that grades across 3 separate dimensions. And then GPT-4 is a few-shot grader that does dichotomous grading. So we provide GPT a few-shot example of correct and incorrect responses, and then asks it to classify. And then finally, my grader, or Blue Bison, these different graders were identified to students by little mascots, is the code generation grader that I've been talking about. So for data collection, we put together a lab activity where students were completing EIPE questions, and they had a variety of auto graders used for each of these questions. And again, these were identified through the mascots, and at the end of the lab activity, we asked students a survey ranking their preference of the different auto graders, and in particular, their preference of the feedback that the auto graders produced. All of the other graders, perhaps as a result of mostly providing dichotomous feedback, with the exception of the three-dimensional grader, which does provide dichotomous feedback, but just across 3 dimensions, students overwhelmingly preferred the code generation grader, and in particular, the feedback that it provided. Kind of referencing what we were just talking about a moment ago with respect to language differences, a thing that I kind of glanced over when I was introducing the grader is a core limitation of prior work on EIPE questions is their focus on English language descriptions. But given large language models are trained on a wide variety of languages, by utilizing a large language model in this grading process, you get multilingual grading kind of for free. So one of the, oh, whoops, sorry, wrong button. It was bound to happen at least once. So it makes these questions somewhat language agnostic with respect to the natural languages that students can provide, of course with the asterisk that it's performing best on fairly high resource languages like Hindi, Chinese, English, Spanish, and so on and so forth. So ongoing work in this area, I have a number of collaborators, in particular in India, which is a context that's very linguistically diverse, on putting these questions onto online platforms that teach introductory computing and evaluating how well it's performing in those contexts. Additionally, oh, go ahead.
I'm just curious, for these sorts of questions, are students graded on grammar?
That's an interesting question. I think that would require a separate evaluation for me to see how grammar is impacting the probability of correctness, I guess would be the outcome there. So it's not.
In terms of like, is the code correct? I mean, this is wrong because it's not grammatical.
Sorry,
like a language description which is not grammatical.
Yeah, that's what. That's why.
wrong because we're in a university and you should be speaking.
No, it doesn't. It doesn't integrate quality of grammar or description into the auto grading pipeline, and they're not given feedback. Yes. Yeah. And then with reference to what I teased a moment ago, in that the auto grading approach doesn't differentiate between multistructural and relational responses. I'm interested in continuing to develop the auto grader to not only understand the difficulties that students have in traversing from a correct multistructural description of code to a correct relational description of code, and building feedback mechanisms that help facilitate that progression. Some that I'm working on now, one is the notion of prompt segmentation, which takes a student's description and maps the segments of the description to the code that segment of the description is associated with, to help facilitate the development of the connection between natural language and how that manifests as code. And then, as I mentioned a moment ago, with the EIPE questions, oftentimes variable names are obfuscated, but if a student is showing signs of struggle and could benefit from a hint, some of these variable names could be de-obfuscated to help students navigate what the code's doing. So I'm interested in both of those yeah.
I'm curious, this seems like a very clever way to help students understand how to basically chunk code and be able to sort of extract high-level kind of meaning of, what is this supposed to do, how do you describe it? What I'm wondering is, in the end, do you have any feeling for how well this has improved their ability to actually write code?
Yeah, I think this might turn into more of a general discussion question, so I'll give a terse response, and I'd love to follow up with you afterwards. So certainly, there have been prior investigations just thinking about this as a code comprehension activity, irrespective of the LLM at the moment, between developing the students. There's a correlation between students' ability to comprehend code as measured through explain in plain English activities, and their ability to write code. So these seem to both be, higher up skills in the skills hierarchy, so to speak. So defining causality there is tricky. Does this cause students to become more proficient at writing code? I think that's a bit of an open question. But with respect to the role that LLMs will play in an intro computing course in the future, or some genre of intro computing courses if there end up being many varieties of them, I think there's a question here of how much code do students need to know how to write in order to be effectively able to do computational tasks with the assistance of an LLM. So if I'm understanding your question correctly, I think the former part that I said probably is more of a direct answer, but I think there's an additional question of here of what are the objectives of intro programming courses going forward. But yeah, I'd love to follow up with you on that, yeah. So yeah, with that said, we're still very much so in the early days of generative AI, in particular in introductory computing courses, somewhat as discussed through that question. So there's this grand question here of, how do we continue to develop and evaluate pedagogical tools in the context of generative AI? So let's take a step back and think just more generally about some of the goals in education research. So there's two settings in which we can develop assessments: formative settings, where we want to develop tools and approaches that support novice students or support students in developing skills and acquiring them. And then summative settings, where we're, in particular, when I say summative settings, I'm mostly thinking about exams, develop assessments that are reliable in evaluating if students acquire those skills. And these kind of go hand in hand. You develop some tools or interventions or curriculum that helps students overcome some difficulties that you suppose they have. You go off to the exam, you see how well they're acquiring these skills. You might go back to your curriculum and help to improve it in order to improve acquisition of these skills, and also reflect on your exam to see if it's actually measuring what you think it is. In the context of computing education research, thinking about, in particular, formative settings first, the barriers to students acquiring skills, some often cited ones, are that they find programming very frustrating, and this makes sense because you go into a text editor and you have limited domain knowledge, you write some code, it doesn't work, you lack the domain knowledge to correct it, and this becomes a cycle of frustration and disengagement. So in general, we want to develop approaches that understand these challenges that students are facing in those early days of programming, to develop tools and approaches that help students overcome those difficulties. So here's my work on one approach, which is a Parsons problem. So Parsons problems, for those not acquainted, is an activity that seeks to scaffold the process of learning how to write code. Much like a traditional code writing activity, we present students with a prompt that's usually a function or segment of code that we want students to implement. But rather than having them write the code from scratch, we present them with blocks of code that they are meant to arrange in order to create a solution. On top of just the correct blocks that students need to arrange, we can also include distractor groups, where distractor is a term borrowed from multiple choice questions, where one of these blocks is correct and required for the solution, and the others are some plausible but incorrect alternatives. So to solve this problem, students drag the blocks over from the left to the right and implement to the function to fulfill the task that we set them to complete. So some of what we know about Parsons problems, so there's a lot of literature showing them to be fairly effective in scaffolding the process of learning how to write code. In particular, they've been shown to be a very efficient mechanism since they reduce that early struggle. And in many ways, what they learn in Parsons problems transfers to the process of learning how to write code. However, in this broader literature of Parsons problems, there was a bit of a gap prior to my work, and that was work that was informing the utility and design of these distractors, which had been included in Parsons problems since they were introduced in a paper in 2006. So broader question of most of my dissertation work has been, what are the affordances of using distractors in Parsons problems in summative or exam contexts and formative contexts? So first, delving into formative context, the guiding question here is, do distractors in Parsons problems help students learn, implicitly compared to Parsons problems that don't include distractors? So I developed an evaluation of this that was aimed at addressing two research questions. The first was, how does practice on a new concept using Parsons problems with distractors compare to practice without distractors in terms of learning gains? And then how do students engage with the two different varieties of problem type? So we did this experiment again in the introductory Python course at University of Illinois that I've alluded to a few times. And in terms of data collection, this was set up as a separate outside of class activity that students were asked to participate in for some amount of extra credit in a proctored environment. For the experimental setup, I used an explanatory mixed methods design, where phase one is primarily concerned with understanding the actual quantitative impact of practice without distractors versus practice with distractors in terms of learning gains. So we did a randomized control trial with two different groups practicing under the two conditions, and then measured their learning gains through a post and retention test. Spoiler, students with distractors did better than students without distractors. So phase two, or the qualitative analysis, is aimed at understanding why that learning difference emerged. How was distractors or some other mechanism causing these learning gains? So there we did think aloud interviews with students interacting with the two varieties of question. And then that concludes with a holistic analysis that brings together the qualitative and quantitative portions to offer a fuller picture on what's going on. In terms of the quantitative setup, or the randomized control trial that was interested in investigating learning gains, students completed a pre-survey on a topic. In this case, it was Python sorting algorithms that, importantly, they hadn't encountered in the course yet. So this was done midway through a semester where they kind of had the fundamentals of Python down, but they hadn't interacted with more of the advanced features. Just to ensure that students actually hadn't encountered these before, we did a pre-survey that showed them segments of code that involved these sorting functions, and asked them to self-report on whether or not they'd seen them or utilized them before. They then completed a reading on the two varieties of sorting function, in particular focusing on the distinction between the two, which is that list.sort does an in-place operation, modifying the original list, and sorted provides a copy of the original list, leaving the original list unmodified and providing that sorted copy. They were then moved into two separate conditions where they were doing the same problems, but one condition had distractors paired with the blocks of code that contained the concept that they were learning, in this case, the sorting algorithm or the sorting functions, and the other condition didn't have any distractors at all. They then took a post-test immediately afterwards, and they were asked to return for an optional retention test, which was done a week later, again, before they'd encountered these functions in the course, and we had 74 of the original 86 students return. So, in terms of the analysis of these test scores, we ran an ordinary least squares regression where we're predicting score on each of these respective tests, the post-test and the retention test. In terms of the predictors, we have a binary variable for distractors, which is the condition that the given student happened to belong to. Two controls for the Likert questions that ask students to self-report on their familiarity with these functions. And a final exam predictor, which was an exam students had taken in the course and acts as a control for general programming ability, since there was likely variance in the two groups. And we didn't do a pretest. In terms of the post-test results, students, as I mentioned before, in the distractor condition outperformed students in the no distractor condition, as indicated by the regression, by about 12%. And that was the condition they belonged to was a statistically significant predictor. Looking more closely and also using this as an opportunity to introduce the varieties of questions that students were given on the post and retention test, we see that in explain the error and fixed code questions, students were doing better. So in explain the error questions, students were shown a segment of code, asked if it contained an error, and then if it did, asked to explain why or where the error was. Fixed code, similar, but students were asked to instead modify the code until it passed a suite of unit tests, and they were given 5 attempts on that. Write code, they had to write a function from scratch that inevitably involved the use of one of these sorting functions. And statement questions were single-line code writing questions that required the use of these sorting functions. So we see the largest gaps in the error identification and fixing areas, but less so in the writing and statement areas. Moving on to the retention test, we see the performance differential shrink. So the group that students belong to is no longer a significant distractor, but the effect size, has shrunk to around 10%. So pretty positive learning gains on the pre-test, and then on the post-test, potentially some learning gains, but they've shrunk, which not bad for what was effectively a 2-hour learning activity. Moving on to the qualitative analysis. So we've seen this performance gap. We want to understand what mechanisms are at play here. Why are students in the no distractors condition not learning as much as students in the distractors condition? So we again devised a reading that involved the use of a function that students hadn't previously encountered in the class. In this case, it was the use of iterating through the values and keys in a dictionary with the .items function, and gave them 14 Parsons problems that involved the use of this function that alternated between questions that did and didn't include distractors, and analyzed these think-alouds with thematic analysis. 2 themes that kind of elucidate what's going on here. First is that students don't always attend to blocks that aren't grouped with distractors. So often students, particularly when we were sampling them in the course where they're midway through a semester, they've acquired some heuristics on what blocks go before other blocks and what programming patterns they might have encountered. So this student, just to read through their description, said definition first, return values last, probably. Have to initialize this for loop conditional and then what it does with the conditional. They got the answer correct on the first tie and then reflected that even without reading the directions, they were able to get that response correct by just looking at the keywords, function definition, return, so on and so forth. Conversely, when a block was paired with distractors, students more carefully looked at the different blocks and compared differences between them. So as the student states, it's tricky to know if it's value and key or key and then value, and if there's a parentheses by items. So in effect, distractors seem to be fairly essential in focusing students' attention on the implementation of a block. And in particular, if you're using Parsons' problem as a mechanism to introduce a new concept and show students how it integrates into some other concepts they might be familiar with, it seems to be essential to pair that with distractors so that they attend to it rather than placing the block without fully reading the block, the code that's contained within that block. I have some future work that I'm interested in investigating in this direction. So a lot of the affordances that I alluded to with Parsons' problems rely very heavily on the efficiency of visual processing systems. So the ability to glance through a whole bunch of blocks quickly, identify quickly small differences between blocks in a distractor group, and just the broader idea of reducing the cognitive load associated with writing code by giving students existing blocks of code. There hasn't been much accessibility research done in this domain, and it's an area that I'm very interested in either improving the accessibility associated with Parsons problems or coming up with new activities that borrow in spirit from Parsons but are more accessible to visually impaired learners. In the context of summative assessments, or in particular, again, exams, the broader question here is, do distractors make Parsons problems better at measuring students' programming skills? So just to give a very quick primer, at least one of the lenses by which we can evaluate items or the quality of items as they're used on exams, there's the lens of classical test theory, where we're generally concerned with reliability, which there's a lot of statistics that go into computing reliability, but at a high level, it's the degree to which there's an assessment is measuring the skills that it purports to, and all the items are cohesive in measuring those skills. Under this, there's a bunch of statistics that inform the quality of the items. Two that I'll highlight are item difficulty. You don't want questions to be too easy or too hard, otherwise you run into ceiling and floor effects. You want them to be in the middle, usually a nice bell curve if you can manage it. And item discrimination, which is the correlation in classical test theory, is the correlation between a student's performance on an item and their performance on the exam as a whole. At a high level, this is effectively measuring the item's ability to differentiate between high-performing students and low-performing students, which, if your assessment is reliable, should correspond to differentiating between students who have acquired the skill and not acquired the skill. And in particular, working to improve the item discrimination characteristics of your questions is often cited as being a key mechanism for improving the reliability of your classroom assessments. So this is going to be a quick tour of what was a multi-semester long project. Oh, there we go. Sorry, my display went out. Where the research question was effectively, how do questions that include distractors compare to questions that don't include distractors, in terms of the amount of time students are spending on the problems and these psychometric outcomes. There's a couple of different interfaces that we can include distractors with. So semester 1, we compared no distractors to jumbled distractors, where the distractors aren't necessarily paired with their correct alternative or other distractors that they're related to. And then semester 2, where we have no distractors and visually grouped distractors, where they're put together in one of these pick one groups like I've shown before. This evaluation was again done in the context of an introductory Python course at UIUC, and we randomly assigned students Parsons problems routinely as a part of the exams. There's a fair bit of randomization in our exams, so we just randomly assigned students one of these questions from each of these question pairs that we came up with. And in our analysis, we use classical test theory and some descriptive statistics. So the 3 outcomes that I'll give an overview of now are duration, the amount of time students are spending on the problem during the exam, which is a concern in a time-constrained setting. Discrimination, which is the item discrimination, or how good these questions are at improving the measurement of the items, and score, which is how hard the questions are. These plots are a fair bit to take in though, so just stepping through them a little bit before we get into the actual results. Each of these distributions are a distribution of differences. So for these exams, we came up with pairs of questions that had the same base solution. The only difference is one included distractors and the other did not. We find the average, in this case duration, for each of the questions in that pair, and each of these dots represents the differences in averages. So we can see how the presence of distractors are shifting outcomes. And then on the right, it's the same thing, but for semester 2, which was grouped versus no distractors. So stepping through this, the first distribution seems to suggest that there's a fair bit of increase in the amount of time that students are spending on these questions, on average around a minute, but upwards of several minutes. In some cases, not represented in this plot, but we saw up to a 200 or 300% increase in the amount of times on the extreme end of things. And interestingly, though the tail does seem to be cut off in the grouped distractors section, just visually grouping distractors with their correct alternatives doesn't seem to have impacted the mean increase in time. In terms of item discrimination, the mean's pretty centered around 0. If I recall from memory, the average increase was 0.04, which isn't very much. So they're not doing much to improve the quality of the exam items. And then in terms of score, they are making the questions more difficult by about 0.5 points or about 10% harder. But in interpreting, in particular, the item discrimination characteristics, Parsons problems with or without distractors were already functioning as fairly good exam items. So they all had discrimination values of above 0.4, which is generally considered good for classroom assessments. Yeah, in aggregate, they don't seem to be having much of an impact on item quality, but are increasing the amount of time students are spending on the exam, which draws into question their actual utility. If you already have pretty good exam items, you could just include another Parsons problem that doesn't include distractor on your exam, and now you have 2 measurement points on that student's ability with a good item rather than adding on a dimension of difficulty that really isn't improving item quality. Yeah?
So for these exam situations, you were in computer-based classroom testing scenarios?
Correct, yeah, sorry, yeah.
And for the non-summative form, were they also in labs like that, or were these like unbounded time scenarios, like in the your initial discussions?
Oh, in the formative context?
In the formative context.
That was still a timed test. So they had around 2 hours to complete the reading and complete the practice activity. So it wasn't unbounded. But with that said, we did look into the amount of time students were spending on the activities, and all students managed to complete all of the practice activities in both conditions to correctness. So Yeah.
I see. So that was that was in a do it until you get it right sort
Correct.
of scenario in
Yeah.
like a section of some sort.
Yeah, sorry, so I missed that context here. So since this is in an exam setting, they had a limited number of attempts. They had 3 attempts to get the question correct, and there was some intermediary partial credit given based on the distance between, the edit distance in effect between the correct solution and the solution they provided. Yeah, yes.
Apologies if you said this, and it's just, I blanked or something.
Yeah.
I don't quite understand what discrimination is as opposed to duration or score.
Certainly, yeah. So duration, since these are done on in a computer-based environment, we track the amount of time students spend viewing a page. So we have some, particularly since this is in a proctored environment, we have some sense that this is probably a pretty good estimate amount of time they're spending on the problem. Discrimination is the correlation between their score on the item and their score on the assessment overall. The idea being that if that discrimination is high, then this item is doing a pretty good job at differentiating between high and low performing students, which is in turn a measurement of that item's quality. And then score is just their performance on the question. So here we see that they do about a half point or 10% worse on questions that include distractors versus those that don't. Does that address or? Lovely, thank you. So yeah, key takeaway here being adding a single group of distractors doesn't really seem to be having a substantive impact, which gets back to that key takeaway that I said a moment ago. If you want to improve, these are already high performing items without distractors. So you could just, if you're comfortable with students spending more time on the exam, you could just include another Parsons problem as opposed to one that includes distractors. There is another question here, though. My previous investigations primarily only used one group of distractors, so maybe there's a point at which this begins to make sense. So my ongoing work is adding distractor groups and seeing how these characteristics differ between questions that don't include distractors versus those that include 1, 2, or 3 groups of distractors. And in this instance, I'm also expanding my the breadth of the questions I'm interested in asking to include things like the quality of the distractors, which is often measured through distractor deficiency, and also using item response theory in this analysis. So switching quickly back to generative AI, again, reflecting on these goals, in formative settings, we want to develop tools and approaches that support novices, and in summative settings, we want to evaluate whether or not they've acquired the skills we were interested in them acquiring. So in thinking about the transition into CS1 LLM and what that's going to entail, we need to reevaluate what summative and formative contexts look like in CS1 LLM. In summative contexts, we need to think about the objectives of those courses and how do you develop exams and exam items that student tests the abilities that we think are necessary in this new context, like is EIP sufficient to test prompting ability or code comprehension ability, or do we need to employ a wider variety of questions to get at these traits? And what other skills might be necessary, like problem decomposition, and how do we assess those? And then in formative context, how do we characterize what a good prompt looks like and provide feedback on poor ones? Again, thinking about my work with EIPE questions. And how do we approach creating tools and activities that support students in engaging in human AI collaborative coding at the novice level, which in part inevitably involves understanding the challenges that students face in those contexts. So with that, here's a quick summary of some of the stuff I've just finished talking about to help guide questions, and I'm happy to take your questions.
So, yeah, okay. So, in this scenario, both the examination methods and the other were in these kind of closed lab settings.
Yeah, all were in proctored closed lab environments.
All in proctored closed lab settings. A lot of things these days not everybody has the luxury of closed lab settings. Yeah. And so what do you see about the handling of Gen AI techniques in those more open settings, and how do we deal with it, and for those of us who don't have that luxury?
Yeah, so yeah, this is something I've been, and I think we've all been reflecting on a lot these days. One thing that I've been fairly conscious of trying to avoid since the beginning is becoming a bit reactionary with how I think about trying to come up with, I think there's a tendency to think of coming up with LLM-proof activities or trying to LLM-proof our courses, which I think as LLMs continue to improve is inevitably going to make courses a bit more human-proof as well, or at the very least novice-proof, which we want to avoid. So my conclusion in this regard has been to, I think a lot of courses are going to shift more towards having more proctored exams and having that be a larger percentage of the course grade as both a mechanism to incentivize students to learn those fundamentals and ask them to demonstrate fundamentals independently of their friends or LLMs or whatever variety of external resources they might have, which I think doesn't actually differ that much from previous approaches or like previous courses. Like students always had Chegg, they always had each other. Now they have an oracle that can answer all their questions, so I'm not pretending like things haven't gotten substantively worse, but I think an emphasis on summative assessments, exams in particular, is going to receive further emphasis. But with that said, something that I'm excited by is hopefully we can incentivize students to develop those fundamentals by giving them these proctored exams and then give them perhaps more engaging projects outside of an exam context. Since having developed those fundamentals, they can now take that and then an LLM is only going to make them more proficient, quote unquote, in their ability to produce more interesting projects. So I think there will be an evolution in that regard. Yeah.
Other questions?
Hi, this is a very interesting talk, and I'm a psychometrician by training, not a computer scientist. So my question may be a little naive.
Oh, no.
I'm really interested in your auto grader and how it actually provides formative feedback.
Mm-hmm.
So can you elaborate on the underlying mechanisms of the formative feedback?
Certainly, yeah. Let me do a little bit of scrolling back here. So just to clarify, this is in the context of the Explain in Plain English activities?
Yeah, so I wonder whether your auto grader is based on LLM, and if it is, did you provide any rubrics for it to provide a formative feedback that is going to be useful?
Yeah. So it does rely on LLMs. Just to walk through the pipeline again, the initial question that students are shown is a segment of code, and then they're asked to explain it, at which point it's just handed off to an LLM of your choice, and it generates code. At that point, the code generation process, my key concern is an LLM's tendency to produce code that is outside the scope of a student's current knowledge. Because if I want this feedback to be useful to students, and I say feedback with a caveat, and I'll get into that in a moment, if I want the feedback mechanisms that I'm providing them to be effective, it needs to be generating code that has knowledge components or things that they're familiar with. So I don't want it producing very complicated code. So I give the LLM some instructions and sometimes some few-shot examples of what code at the level I would expect students to be able to write on their own or at least interpret on their own is within the context of the course. And at least anecdotally, I've spent a lot of time scrolling through code that's generated from this grading process, and I haven't seen any instances of it going outside those bounds, which is something that it would occasionally do with older LLMs, but these days it's pretty reliable. With respect to the feedback itself, yeah, so they're shown this, it gets sent off to an autograder and they're provided feedback pretty much immediately. The two modes being, one is the code that's actually generated, which I just finished talking about, and then the results of test cases themselves. I'm interested in the future in hopefully providing some more adding layers onto this that help direct students in how to utilize that feedback and potentially adding additional feedback mechanisms on top of it, because it's not necessarily clear to students, though they did have those emergent patterns of diffing and looking at the input space and seeing what test cases they failed. Since these are novices, I want to build out a wider variety of support mechanisms as well.
Yes, thanks for the explanation. Just piggyback on this a little bit. So did you fine tune the LLM model for such purposes, or did you give them a few shots learning just so that it learns how to generate useful feedback?
So in this context, since it's just providing the generated code as one mode of feedback, I didn't do like any substantive fine-tuning or modification of the model. Most benchmarking studies show that particularly OpenAI's models and Meta's Llama models are very proficient at generating Python code. So I didn't have too many concerns that it would need substantive fine-tuning in order to produce this variety of feedback. Thank you.
Others? Oh.
Hi, I'm not sure if this is within the scope of like the pipeline that you described, but like I know you're describing how you want to be careful about the output and have it not like be something that's not at the level that students are learning. But has there also been consideration about the input to the LLM? Like, let's say a student just copy pastes the code and then says that's their description. Have there been considerations around that?
There are, yeah. So referencing this, direct recitation and multistructural are kind of, direct recitation in particular kind of gets at what you're talking about, which is copy-paste. Though here students, we disabled copy-paste for these questions, like it won't let students highlight the actual code. And so students would be typing it out and then inevitably have a few errors or typos in their description. So there's not a robust prevention mechanism in this baseline model, but to tease some upcoming work, I've been looking at some modified grading mechanisms that can be layered on top of this. In particular, the idea of prompt segmentation, where you take a bit of a student's description and map it to a bit of the generated code. It seems to work reasonably well, and in particular in the context of students copy-pasted code, the mapping that would be produced is this line of code is this line of generated code. So you end up with a lot of segments. So if this feedback mechanism's intention is to guide students towards having fewer segments and therefore having more relational responses, hopefully this would be one mode of providing feedback and differentiating between those two outcomes. Because there's perhaps not so much copy-pasting, but since this is used in a formative context, I want to escape this binary grading universe that we previously lived in with EIPE questions and think of this as more of a progression, where a multistructural correct description of code is still a correct description of code, and we just want to move students from multistructural correct up to relational correct. So if a student provides that variety of response, they can say, yay, you passed the test cases, but there's still some refinement that we're going to do on top of that in order to build your comprehension skills.
Oh, hi. I think I have the next question.
Yeah, thank you.
I was curious why in your study you decided to focus on EIPE and Parsons style problems instead of maybe other types of problems?
Interesting question. Yeah, in the context of Parsons problems in particular, it was mostly down to that. I suppose this is a bit more of a story then. So I got into my research with Parsons problems as a result of my teaching experiences as a graduate student. So I was teaching a large intro programming course, and I spent a lot of time authoring questions, and as a result, thinking about what my intention is when I author a question. And I was familiar with the broader literature on Parsons problems and what made them effective, and that they were pretty good as exam items, but I noticed the gap in the use of distractors. So I went about, I was aware of some, because a lot of my work is just focused on assessment in general, even outside of computer science contexts. I was aware of a lot of the literature that existed with respect to multiple choice questions and things that informed the creation of good multiple choice questions. So given the gap in Parsons problems and my knowledge of that space, I set about figuring out how to generate distractors, which isn't represented in this talk, but I did a bunch of static analysis of common errors that students make when writing lines of code in order to generate my distractor template set with the intention of making these realistic errors, which I think is particularly powerful in a formative context where I want students to encounter errors and distractor blocks that reflect the types of errors they might make in practice, and then went about evaluating them in both the summative and formative context. And then similarly with EIPE questions, in teaching these courses, I want students to develop code comprehension abilities, and my general research philosophy, or my teaching philosophy is I want students to have as much practice as they desire, which means lowering the authoring overhead of questions, and in particular making effective feedback, which means improving the feedback mechanisms that they can get, which was a gap that existed with explain in plain English questions. So that led to the development of that auto grader, and the kind of ongoing integration of LLMs into intro computing has continued that work, since I think those questions are finding new life in that context, since this work has yet to be done, but hopefully exercising the process of generating these descriptions of code might help students create good prompts to further develop their ability to engage in human Gen AI collaborative coding.
Any others? All right. Just speak real loud over.
Yeah, walk over. Just, call attention we having a loud voice.
I can come over there with my lab mic and lean over.
No. Quick question is, so it seems like when you change these explain in plain English questions to explain to an LLM, it fundamentally changes what people are doing, in that they are trying to use an LLM to write code rather than communicate to a person. Have you thought much about how that shift changes things? I mean, this is an expansive question, so hopefully
No. It's interesting. I like the phrasing of the question, like explain in plain English, like communicate it to a person. And I guess here I have an anecdote that I think this is a difference that exists fundamentally between manually graded responses and auto-graded responses, and exists irrespective of the particular machine learning approach or other auto-grading approach that you happen to be using. Because with the NLP grader, the logistic grader that we'd used previously in the course, I taught a high school instance of the intro computing course where I had 14 students, and I got to observe them completing these questions as a part of their in-class activities. They started to develop folk theories on how the auto-grader worked, and I started to see they kind of surmised that it was looking for keywords, since it was trained on a bag of words thing, and I started getting responses that were just keywords in effect, and it was fun to see them reverse engineer actually reasonably accurately what the grader was doing. And I think something kind of exists with the LLMs. Like, I'm sure there's a shortest response wouldn't be easily interpretable by a person but could produce correct code from an LLM. So this is going to be a problem that I think manifests in any auto implementation of an auto grader. And there's a cost benefit here. They might not get feedback that aligns. The auto grader might always have some dimension in which it's providing students a grade of correct on something a human would regard as incorrect, but they're able to get more practice and immediate feedback, which is valuable in a formative context. Whereas with the human manually grading approach, they might get more accurate feedback under the learning objectives we're asking them to demonstrate, but that feedback is going to come sometime after any difficulties they happen to have, which deters their ability to, or makes it more difficult to remediate on those particular problems that they're having. So certainly I think I need to understand that in this particular auto-grading context, but I think it exists across all auto-grading contexts. Thank you so much.
So before we thank David for his excellent talk, I want to note there is one opening available in his schedule tomorrow. So if you want more and want to talk about this stuff more with him, it's not too late to sign up. But for now, thank you very much, David.
Thank you so much.
And thank you everyone who attended.